of 4 technicians, and installations and removals, if required, are very, very easy because the system are connected without valves or holes on the rails, but it takes each component takes about 5 to 10 minutes for connection to the rails. And before coming to an end about the general introduction of the system and general descriptions, I would like to put a few more points about the features of the system. System is also capable of detecting landslides, floods, excess snow accumulation, and train movements on each segment is easily monitored, and the moving trains speed are also easily monitored by the system, and the train wheel flats are also detected easily by the system, by the same system. This system runs all these algorithms all together without any modifications or changes into the existing system components. And the critical thing is initial conditions of the acoustic properties of the track is critical. As we take all those measurements initially after the first installation, any change coming because of the landslides, floods, snow accumulation is easily detected. So you know, other than broken or faulty or fractured rails, especially because of these quick change in the weather patterns in Turkey, we have a number of actually critical threats like landslides and floods. They are also critical parts of the detection parameters of the system. We use them heavily. As I come to the end of my presentation here, I would like to basically talk to you about our company. We are running Enecom as a basic research and development company on railway technologies, and we are the inventor and developer of the technology, and we have got 8 patents, and some of them are internationally acknowledged, registered. The company is located inside Middle East Technical University, Technopolis, and that's why we have very heavy interference with university research and academical staff, and industry is also our cooperation scope, and we also focus on some optical and spectrometric railway detection technologies along with rail acoustic. And I would like to thank you for your patience and interest on watching and listening to us, and hopefully I can answer all your questions regarding the technology and further details. We would be all happy. If you need to go into further details, you can contact us after this presentation if you like. We will be also happy to answer all your queries. Thank you very much for your time.
Thank you, guys. Just so everybody knows, I started recording late, and I think I'm legally obliged to ask your permission to record this presentation. So if anybody has a problem with that, please let me know, and I will delete the recording, but otherwise I would like to make it available to others. And I do have a couple of questions. Can you tell me the 2-kilometer maximum spacing? What is it that governs that? Why couldn't it be 4 kilometers or even longer?
Okay, actually, physically, we are quite interested to find out smaller and smaller fractures or faults inside the rails. You know, we can easily go up to 3 kilometers. But I mean, naturally, there are some limitations, physical limitations of the detection technology we are using. We have developed this technology, but there are some certain physical limitations. The acoustic waves, they propagate longitudinally on the inside the rails, but as every few hundred meters, they decay to a certain level with a certain exponential rate. So that way, there is a physical limitation. And there is a further study about new techniques or new technologies of utilizing for the detection. But currently, there are certain reasons for these 2 kilometers. One of them is physically, the system is in need of focusing on little more smaller faults inside the rails. So we limited the distance, the maximum distance to 2 kilometers, especially, you know, instead of deciding only about the brakes, we are more interested these days about finding out smaller or inside the rail faults that they need to be more accurate, and more accurate signal needs to be taken by the detectors. And because of this limitation, we have decided to go up to 2 kilometers. In fact, around switches, we naturally go down to 500 meters or 400 meters sometimes, because there are a number of repetitions of, you know, change in the physical conditions of the junction points on the switches. So we can say, you know, between 400 meters to 2 kilometers would be most optimal for standard high-speed line, standard railway track. In the future, we might go up to 4 or 5 kilometers, but this model is most suitable for up to 2 kilometers.
Okay, and that's what your response was a little bit of a segue to my next question, was if you can detect, you know, you showed a slice in the rail, so you could detect internal defects, transverse defects, and yes, maybe even cracking that is propagating into the rail?
Right. Actually, any surface created inside, you know, a kind of fracture inside rail is also detected by the system. But as we go in longer distances, they need to be bigger and bigger. And naturally, we have got this kind of consideration about inner faults instead of only concentrating on the brakes or major faults. Major faults are easy, and we are definitely looking to longer distances. But as we are more interested also, you know, before the accident or before the major interruption on the physical structure. So we need to go a bit, you know, shorter in this distance. Currently, it looks like a maximum 2 kilometers is the most optimum distance we have to locate each node of components on the track.
Right. Okay, we can open it up for questions. If anybody else has questions, you could use either the chat feature or use the audio.
Right. One thing, actually, Eric, you can, if you have recorded, you can use the recorded presentation for future use and for other inquiries. So no problems about that. And you know, if you like, we can even provide more material about further details of the technology. And you know, we are quite happy about providing all those things as much as you recorded. You can use all those materials as well. No problems.
Mm-hmm. Okay, thank you.
No
we do have a few minutes left. Does anybody want to ask any questions online here?
I have one question. This is Ali Tajadini from FRA. So we have a signal generator and we have a detection system 2 kilometers away. What is the effect of if we have a car moving? What is the effect of the wheels? Doesn't the wheel, or if you have especially some issues with the wheel, like wheel flat or shells on the wheel, does that introduce any noise or any issue with your system? How do you handle that?
You mean the train, or you know?
Yes, the train.
Track? Yeah, okay. Actually, the tests are you know, supposed to be done before the train comes. Now, naturally, an accident prevention strategy needs the system to operate before braking time of the rail moving vehicle comes to the area of the fault. So in that case, as the tests are initiated by the central command computer under computer command, and the times are pre-scheduled according to the moving trains. So we receive the vibrations coming the trains. That way, continuously we monitor the moving trains on the track, and we locate their position. That is another function. But for preventing an accident related to a broken segment, these tests are performed before the moving vehicle's arrival to the site. So that way, there is no interaction in that sense. But as assume that a train is coming, it is 400 meters away, a high-speed train is coming to the area. If any break happens at that moment, it would be too late to stop the train anyway because of the braking time. In that sense, from our experience, most of the breaks are happening in extreme weather change conditions, like from night to the morning, for example. And anything after a train passes, and any condition generated by one of these conditions are supposed to be detected before the train reaches to the faulty area. And most of the times, those kind of conditions would prevent detection algorithms would prevent an accident. Mm-hmm.
Okay, thank you.
No problem. And before any broken segment, it goes into a fractured stage, and we detect fractures as well, not only the broken segments and the fractures. So a fracture can go through a full crack in time, because of the weather conditions, or those kind of forces affect the fracture to become a full broken segment in time. So all those conditions are monitored all the way. We follow up all those fracture advances inside the rail, and before it comes to the level of a full break, we raise alarm, and naturally we avoid the risk of an accident happening. Does that answer your question?
Yes, thank you.
No problems. Thank you very much for the question.
So basically, you're saying on the segment, you should not have any movement. You should not have any train moving there.
Yes, I mean, the train doesn't affect. I mean, train is also a natural vibrator, so we can utilize those signals as well for detecting. But the effective strategy should be before the train. Before that.
Okay.
Very close. Yeah.
Thank you.
Mm-hmm. Any other questions? And actually, I would like to iterate one point, actually, in addition to the existing railway brake sensing technologies. This system, in opposition to the electrical sensing mechanisms, doesn't look for electrical continuity of the rails. Before a rail break happens, for example, breakage on the rail head can cause to an severe accident. The system doesn't need the system to break apart totally, but a major fault can easily be detected because of the system's acoustic properties change severely, and that way even a train can pass through without an accident, but still we find out those kind of faults as well before the train reaches to the faulty area. And